GCSE Physics boosters, electromagnetic waves. Now, this is a big topic. I'll be doing about 3 or 4 videos all about electromagnetic waves and light in particular. This is important. This is an introduction to electromagnetic waves. Wow, lots of pictures. Now, what's going on here? If you know anything about electromagnetic waves, you should have done it in year 9. You should realize that these pictures represent the different types of electromagnetic wave. Let's have a look. Starting top left, we have a radio. We have some radio telescopes. Next to that, we have a microwave oven and a mobile phone. What's that got to do with microwaves? Next to that we have a little lamp, and it's being kept warm with an infrared lamp, and later on when it's a nice shepherd's pie, that can be kept warm with an infrared lamp as well. We have a TV remote control. Next to that we have a torch, we have a rainbow, some nice Roy G. Biv going on there. Bottom left we have a money checker, something glowing on that £20 note. Somebody getting a suntan on a sunbed. Next to that we have a skull, the bones in your head, and we have looking inside somebody's luggage using an X-ray machine. Uh-oh, there's a gun. Uh-oh, never mind. And then next to that, bottom right, we have a gamma camera. And we also see food being blasted with gamma radiation to kill off germs and bugs and things, so it lasts longer on the shelf in the supermarket. So lots of different types of electromagnetic wave, and they have different properties and they have different uses. Now, what is an electromagnetic wave? You don't really need to know this, but it's interesting. It's basically an oscillating electric field and an oscillating magnetic field. If you do A-level physics, you'll learn more about it. What you do need to know is what they have in common. Now, all these types of electromagnetic wave, they are transverse. They can travel through a vacuum, so they can travel through space, and they travel at the same speed in a vacuum. And that is little c, 3 times 10 to the 8 meters per second, which is very interesting. It's the universal speed limit. Nothing can travel faster. Differences between them. Now, it's a continuous spectrum. So you've got like very big wavelength going all the way to very, very small wavelength, and it is continuous. There are no gaps in it. But what we have done is we've put it in groups of waves that we've given names to. And basically these groups have about the same wavelength, and they have certain properties and uses. Okay, so the groups have different wavelengths and frequencies as well. If the speed is the same, if the wavelength is different, then the frequency has to be different, doesn't it? V equals F lambda. Right, so these are the groups that we have put them in. Starting with the biggest wavelength, which is the lowest frequency, radio waves, then microwaves, then infrared, visible light, ultraviolet, X-rays, and gamma rays. Gamma rays have the smallest wavelength and the highest frequency. Now, you should learn that list. There's all kinds of acronyms you can use, but get that learned. Radio, microwave, infrared, visible, ultraviolet, X-rays, gamma. I say they have different wavelengths. What kind of wavelengths are we talking about? Well, now radio waves can have big wavelengths, like several kilometers. Okay, typically their wavelength is a few meters. The wavelength of radio 2, I believe it's about 3 meters, but they can have very, very big long wave radio, several kilometers. Microwaves, typically a few centimeters. The microwaves in your microwave oven are about 12.5 centimeters. Infrared is typically a few millimeters. I'll talk about visible in a minute. Ultraviolet, about 10 to the minus 8 meters. It's about the size of 100 atoms. X-rays, a lot smaller. The very smallest atoms, a hydrogen atom is about 0.5 times 10 to the minus 10 meters. So about the size of the smallest atoms. And then gamma rays, tiny, tiny, about the size of nuclei. Very, very small gamma rays, very small wavelength, very high frequency. The higher the frequency is, the more energy they've got, which is why when you get to ultraviolet X-rays, gamma rays, the chance of it giving you cancer gets more and more. They get more and more ionizing, which I think I've talked about in another video. Now, visible light is actually a very small part of the spectrum. Okay, but it's special to us because our eyes can detect it. We can see it. Within that very small part, Roy G. Biv. Now, there aren't actually 7 distinct colours, but we can thank Isaac Newton for this because he was heavily into the number 7. Red, orange, yellow, green, blue, indigo, violet. Okay, so we see different wavelengths within the visible spectrum. We perceive them as different colours. And there's my little friend, Roy G. Biv, the magical elf. I'll put a link to his video in the description. Here's a question to finish for you to have a think about. What types of electromagnetic wave does the sun emit? And how do these types of radiation affect us on Earth? If you want to have a think about that, pause the video. I'll show you the answer in 3, 2, 1. And here we go. So ultraviolet. This is why we get a suntan. We get a suntan on a sunny day because of ultraviolet radiation. If you're not too careful, it can give you skin cancer. There is a thing up there, thankfully, called the ozone layer, which stops most of the ultraviolet getting through. A lot of people worried about the ozone layer. Visible light, obviously, this is why we can see the sun. This is why we can see just about everything. Plants get the energy they need for photosynthesis from sunlight, and we can use it to make electricity using solar cells, solar panels. Infrared. We can feel it as heat, so it keeps us warm, feels nice and warm on a sunny day. The land and the sea absorb and emit heat radiation differently, which causes weather, and I could talk about that for a long time, but I'm not going to. Small amounts of other electromagnetic waves are emitted, but they don't really affect us on Earth.